This is example problem number 5. Here I have a cannon shooting a projectile out at 100 meters per second at an angle of 60 degrees with the ground, and I want to know how far away did the cannonball land. Well, one of the things I can think about in this problem is don't over-examine what the problem's doing. So for example, this projectile is going to land at the same height it takes off from. So because all that distance is so big, we're going to ignore this height here of the cannon itself where it came out. So that is not going to matter to us. Alright, so when I'm starting this, I've got this projectile coming at an angle before I start looking at my table. So just as a reminder for our table, I have vertical and horizontal givens, and I have all of our kinematics variables on the left. That's Vox TVA, VOXTVA on the left. I have a vertical column and a horizontal column. And then vertically, I'm going to have enough variables where I'll use my whole arsenal of equations for kinematics to solve. Horizontally, the acceleration is going to be 0 horizontally. So because it's going to be 0 horizontally, the only equation that's going to work for us is actually the first equation, x equals x naught plus v naught t plus 1/2 at squared. Well, but the a is going to be 0 and x naught is going to be 0, so that's going to turn into x is equal to v naught t, which we're just going to call the range equation. So range is equal to v naught t using the horizontal givens. Alright, so now let's get started. The first thing I need to do is I need to take my initial givens and break them up into horizontal and vertical components because I don't have any diagonal columns here. So what I'm going to do is I'll look at it this way. I've got my initial velocity here of 100 meters per second, and I've got my angle here, and there are the two components right there, and there's my angle, 60 degrees. So I know this side is going to be the hypotenuse times sine 60 because it's opposite the angle. So that's 100 meters per second, don't forget the units, sine 60 degrees, and the side adjacent is going to be 100 meters per second cosine 60 degrees. So now I have my components and I can start filling in my data table. So all the things that are vertical, alright, everything that goes up and down, that's going to be 100 meters per second sine 60 degrees, that's going upwards. I'm not looking for a distance, I'm looking for the range going all the way over. Time, no, I'm not given that. Let's see, acceleration is going to be negative 9.80 meters per second squared, and it's negative because it's going the opposite direction of our initial velocity. Horizontally, I have only that horizontal component of the triangle. That's going to be 100 meters per second cosine 60 degrees. And that's just going off to the right. Alright, so that's all set. Now I want to figure out how far away it traveled. I do know one other thing that I missed. See, in this kind of projectile motion, what's going to happen is our projectile is going to start, let's see, here's the ground. It's going to go here, and then it's going to come back down. It's going to land on the ground. So it's going to land where it's the same height where it started from. So that means that x is going to be equal to 0. The displacement is equal to 0. Well, now it looks really easy. I can look at the top equation here, and I can say that x equals x naught plus v naught t plus 1/2 at squared. And I don't know why I'm actually writing all that out. Let's do this. Let's just throw in the numbers right away. So in this case, 0 is equal to x naught, which is 0, plus v naught t. In the vertical column, that's going to be 100 meters per second sine 60 degrees times t plus 1/2 9.80 meters per second squared times t squared. So in this problem, I've got t and t squared. That means I'm going to use the quadratic formula to solve. But now I'm thinking, I wonder if there's another way that's easier. And there is, to use another way that's easier. See, here's what I know. This motion is symmetrical on both sides. So if I think about it right here, kind of in the middle, my drawing's not the best, but in the middle, I know that the time up to this high peak, which is the apogee, apogee is where it's the farthest away from the Earth, and the time down from apogee, that's going to be the same time because of the symmetry. I also know the distance over to apogee is the same as the distance from apogee to where it lands. So I have some symmetry going for me. So in terms of the symmetry, I also know this. I know that the time to apogee, because of the symmetry, is equal to 1/2 the time it's in the air. Now, the reason why this is really nice is because at apogee, the vertical velocity at apogee is equal to 0 because it stopped going up and it hasn't quite gone down yet. So the vertical velocity is 0 at apogee. So what I can do is I can change up the problem just for a moment. And for a moment, what I'm going to do is I'm going to ignore this and I'm going to make that equal to 0. And I'm going to make a little note right here, just that I'm talking about apogee. So I'm not answering the question yet. I'm just talking about apogee. All right, so at this point, what I can do is I can find the time to apogee, which will be an easier setup, and then I can find the range using that time because I know that time is half the time in the air. So let's go ahead and go for that. All right. So let's see. I'm going to use the V equals V naught plus AT equation, and I'll isolate T. That's going to be V minus V naught divided by the acceleration. Now with my numbers in here, let's see, the final velocity at apogee, remember I'm not answering the question, just think about apogee. Vertically, it's going to stop going up and stop going, it's not going down yet, so that's going to be equal to 0 minus the initial velocity vertically. So I'm getting all these givens from my vertical column. So that's where all the givens are coming from here. That's 100 meters per second sine 60 degrees. All that's divided by negative 9.80 meters per second squared. And when I do that, I get a time of, let's see, 8.83699 seconds and some more decimals on it. So if I double that time, that's going to be the time in the air. So the time in the air is actually equal to 17.67389878 seconds. Whole lot of decimals there, but I want to keep them all because it's an intermediate calculation. Now I need to find the range, and the range is going to be the total time it's in the air from where it starts all the way over to where it lands. That's going to be the range. So I got to use the time it's in the air. So I'm going to use the 17.67 to figure that out. So I'm going to leave my color change here and go with this. The range is equal to V naught in the horizontal direction times the time. So I know the time in the air is equal to, let's see, I'm going to go ahead and write this up here just for a moment. 17.67 seconds. And if that's the time in the air and I have the velocity, I can just multiply them to get the range. So the range is equal to horizontal velocity, 100 meters per second, cosine 60 degrees. Notice the units are still there, and the time, 17.67 seconds. And of course, I'm keeping all my decimals, I'm just not showing them right here. But the range, which is the ultimate answer to the question we're looking for, with 3 sig figs would be 884 meters. Okay, quick recap. When we start the problem, we have our usual table that we use for projectile motion with Vox TVA, with vertical and horizontal. But before I fill out anything, before I look at the questions, I look back at my givens and I see that I have that the cannon is launching everything at an angle up here. So here's our angle. So what I need to do is break that up into horizontal and vertical components using trig, and then I'll put those components in for the velocities, the initial velocities, into our table of givens. And then I'll go ahead and I'll start solving the problem. The trick I used in here was realizing some science instead of using some math. And it's the fact that I've got this projectile that's going to land at the same height it takes off from. And this only works when it's landing at the same height it's taking off from. And what I know is that the time up to apogee, which is the highest point of the motion, is equal to half the total time in the air. But at the highest point of the motion, the final velocity is equal to 0. And since the final velocity is equal to 0, that's going to make the math really easy. So using that, I used our first equation over here, with v equals v naught plus at, went through and solved it to get the time to apogee, and then I doubled that time to apogee to get the time in the air, and then I used that time with all the decimals in my range equation to finally get my range of 884 meters.